Hello everyone and welcome to AIME Improvement. Let me just check if it's recording. Right, cool. So for those of you who don't know, this is just um, a short mini video lecture series that ties in with each week's TJAIME topic. Um, and so this first week's topic is PIE. So for those of you who don't know, PIE is the principle of, sorry, inclusion, exclusion. Right, so what does this mean? This is a fancy way of just representing uh, like really Venn diagrams. Like I usually just think of it as Venn diagrams, counting the size of a big Venn diagram. So what does that mean? Well, let's take an example. I think an example is the easiest way to see in this case. So suppose that in a classroom, 5 people like pie. So they like pie. 4 people like, I don't know, sandwiches. And 2 people like both. So, and suppose nobody likes neither of them, so everybody likes either pie or a sandwich. So how many people are there? Well, we might think, okay, we just add the two, right? Number of people. Uh, Number of people who like pie plus the number of people who like sandwiches, right? Well, this isn't quite true because think about the number of people who like both. If we draw a Venn diagram, that just means that the size of this Venn diagram is 5, the size of this Venn diagram is 4, and so we count this area, the stuff on the left circle, in the left circle, and this area, the stuff in the right circle. But there's some overlap. And do you see how we counted it twice? And so because of this, we actually need to subtract out once the number of people who like both. And so there are 7 people. Um, so like here we counted twice, and so we subtract once, and so now we count it once, and we're all good because everything's counted once. So let's take a look at this overall formula, this general formula. We can see, okay, well, let me first define a couple things. So we say we have a set A, right? Then we can say, okay, the size of this set is written like this. This is just the size of A. It's just the number of elements in A, number of things in A, the number of people who are categorized as A, whatever, right? So that's what size is. So let's take a look at this formula. Let's take a look at n equals 2, right? Like this is for any arbitrary n. Doesn't really matter. Well, what happens when n equals 2? Then we actually have uh, the number of things that are in either A1 or A2. Again, these are just names, it doesn't really matter. It's equal to, well, this summation, the number is just the sum for each set of their size. In other words, for each set, we add in its size, and then we subtract out the size of every pair. And in this case, there's only one pair. And this is intersection. So what this reads is the number of things that are in either A1 or A2 is the number of things in A1 plus the number of things in A2 minus the number of things in A1 and A2. And that's the general gist of PIE. Let's take a look at n equals 3 before I say any more on this. We actually have, okay, suppose we have 3 things, like 3 sets, right? And we want the total number of things that are like in at least one of them. So the number of things in A1 or A2 or A3. Well, it turns out that this is just the number of things in A1 plus the number of things in A2, right? Looking similar to this so far. Plus the number of things in A3. So far it's pretty intuitive. And now we subtract the number of things in A1 and A2, right? Still looking pretty similar. But now we have more pairs. We actually have 3 pairs. So A1 and A2. And then we also subtract out the number of things in A1 and A3, and we subtracted the number of things in A2 and A3. And then we're still not done. We still need to add back the number of things that are in all three sets. So do you see how the pattern works now? We start with, okay, we have one thing, and it's positive, it's a plus, and then we have every pair, it's a minus, and then we have every group of three, and it's a plus. And if we continued on, if we had, like, say, 6 sets, then we would subtract out this total. Like, we sum across every group of 4, and then we subtract that out, we sum across every group of 5, we add that back in, we sum across every group of 6, we subtract that out. So that's the pattern. And we can see this, actually, in the n equals 3 case with another Venn diagram, right? Like, I'm just going to write the number of times we count each thing with a tally. How do I want this? Right, so when we add all of these, right, A1 plus A2 plus A3, A1, suppose this is A1, this circle, the top left, A2 is the top right, and A3 is the bottom. Then when we count the size of A1, we count this once, this once, this once, and this once. Then we count A2, this once, 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 once. A3, we count this once, we count this once, we count this once, we count this once. So if we just left it as is, notice how we counted everything in this region twice. We counted everything in this region 3 times. Everything here twice, everything here twice. That's not good. We want to count everything once. So to fix this, we say, okay, now we're going to subtract out every pair, right? So we subtract once, we uncount each thing that are in A1 and A2. So I guess I could do something along the lines of this. Right, so that's gone, and that's gone. And then we subtracted the number of things in A1 and A3. So that's gone, and that's gone. And then we subtracted the number of things in A2 and A3. That's gone, and that's gone. So on the plus side, what we've actually done is now we don't have any overlapping, like we don't have any double counting, but we haven't counted this middle region yet. So to fix that, we just count it again. Boom, PIE, that's how it works. So let's jump into a practice problem in the handout, which if you want, you can actually find on shameless plug, tjvmt.com, and then you can go into archive, and you'll see a bunch of drive folders. You just go into the 2019-2021, and there you should be able to find all the TJAIME handouts, and TJ USMO if you really want. But anyways, let's look at this problem. I have 6 different pieces of candy. How many ways can I distribute them among 3 kindergartners such that each kid gets at least 1 piece of candy? So you could do casework. You could say, right, let's say we have kids A, B, and C, and then we want to give them, like, split up 6 pieces of candy, and we can say, okay, what if person A gets 4 pieces, B gets 1 piece, C gets 1 piece, count that, 3, 2, 1, count that, right? Like, nah, let's not do that. Instead, let's use PIE. Like that way actually turns out to not be too bad, but for the sake of example, let's do PIE. Because sometimes you have to use PIE, or at least that's the cleanest way. So let's actually say, right, we want sets, right? So let me actually say A1, A2, and A3. So we define the size of A1, right? So, okay, what are we counting with A1, A2, and A3? Like what, the first thing you have to do in PIE is say, okay, what are my sets? Well, I want to say this set A1 is all the ways for kid A to get no candy. Now you might think, okay, wait a minute, doesn't every kid get at least 1 piece of candy? Well, I'm basically saying, okay, ignore this first. Okay, so how many ways can I distribute them among 3 kindergartners? No restrictions. So that's A1. And similarly, A2 is the number of ways for kid B to get no candy. And we define this similarly for C. Now, why do I do this? Well, what are we looking for, first of all? So suppose we look back onto here and then we say, okay, well, now we want it. Well, um, what exactly do we want? Well, let's say, okay, the total number of ways with no restrictions, right? Minus the number of ways for either kid A to get nothing or kid B to get nothing or sorry, this should all be union, or kid C to get nothing, right? So if we think about a good way as every kid gets at least one piece of candy, it's pretty fair, right? And then a bad way is just someone gets nothing. They're opposites, right? Like every situation has to be either one or the other. And so we count the total number of ways, and then if we subtract out the number of bad ways, we should get the number of good ways. So let's start applying PIE. Well, let's think for a second. Right, so we know that by PIE, this value, the size of all their union, is equal to the size of each of them individually minus the size of every pair of them and then we add back in the size of all their intersection. So how do we count them into each, right? Like this is what, 7 things that we want to count plus the total number of ways. That's 8 things we want to count. This is not looking much better than the casework. But we can actually abuse symmetry, and that's going to be a key factor in PIE. So what can we say about the size of A1 and the size of A2? Well, A1 is just every way for kid A to get no candy. A2 is just the ways for kid B to get no candy. Well, what if we renamed the two kids? Like the kids are all the same, right? Like we don't treat them as indistinguishable, but like it's symmetric. That's what I'm trying to say. So that essentially says, okay, because kid A and kid B, like it's just naming, right? Like we can just flip-flop the name however we want. That means that these two must be the same, these two must be the same, so all 3 of these must be the same. So that means that by symmetry we can say that the value is also equal to this. And so now we only have 4 things we need to count. And these are all end up being easy. So let's actually start up with all 3 of them. So this is if, so A1 and A2 and A3 is if kid A gets nothing, kid B gets nothing, and kid C gets nothing. How many ways are there for this to happen? Well, it's not possible, right? Like we have 6 pieces of candy, we want to give them all out. We don't like candy. That's for kids, so we're going to give it to the kids. And so like we have 6 pieces of candy, here nobody gets anything. That's not a possible configuration. And so there's 0 ways. And so here, so let's consider this intersection of 2 of them. Well, this case is if kid A gets nothing, kid B gets nothing, and kid C gets something. Well, again, we want to get rid of all our candy, so let's give kid C everything. That's the only possible way. And so each of these is just one way. Now the harder one would be the size of A1. But again, it's not too bad. So the case A1 is just kid A gets nothing, kid B gets something, kid C gets something. Well, in this case, again, kid B or kid C could get nothing, right? Like we don't care. The only thing we care about is A gets nothing. Kid B could get nothing. Kid C could get nothing. They can't both get nothing, but one of them could get nothing and the other one could have everything. And so the way this works then is if we consider each individual piece of candy, this could go to B or it could go to C. This could go to B or it could go to C. And so each candy is independent and we could give each of them to either of them, either kid. And so there's a total of 2 to the 6. and that's 64 ways. And so putting it all together, we have from this formula up here, okay, maybe you can't see it, but the 3 times, right, so just here, actually, that's enough. 3 times the number of ways, so the size of A1, and that's 64, minus 3 times the intersection of any 2 of them, plus the intersection of all 3, and this gives 192 minus 3 is just equal to 189. So now we're almost done. So let's clear out some room. Right, so now we have this, is 189, and now we want to see the total number of ways. Well, the total number of ways with no restrictions, so any of them could get nothing. Similarly to the number of, like when we calculated the size of A1, well, that's just each candy then could go to kid A, kid B, or kid C. And so we have a total of 3 to the 6 is 729 ways. So this is equal to 729 minus 189 equals 540 ways. So something I want to bring to your attention is, notice how earlier, I deleted it now, but earlier I had set up these A1, A2, and A3, and I wrote them explicitly out. This could potentially be important. Sometimes people get tripped up by saying, okay, I'm just gonna randomly define all these different sets, right? Like, I don't really care. Just PIE is intuitive, yay, right? It's easy. But there's a trap there. If you're not careful, you could end up doing something wrong there with PIE. Like, as you get more sets, as you get more complicated conditions in the problem, you essentially, you'll get tripped up. That's what I'm trying to say. And so to avoid that, it helps a lot to write out these actual symbolic notation, right? Like we want to define each of our sets, and then we want to say, we want to write out, okay, this entire union is equal to each, like these sets, and then minus every pair, and then we're going to calculate each of these explicitly. We're going to take advantage of symmetry when possible, but we will recognize when it's not. So that's my PSA. Hopefully it'll help you guys avoid making mistakes. And that's the conclusion of this AIME Improvement video.